Hi, hello, how are you? Craig Chapman here with part 6 of this video series on experimenting with neural network simulation. In this video, we're going to briefly revisit some of the math involved in our 3-layer perceptron network, and this time we're going to be looking to simplify the calculations in preparation for refactoring and simplifying our code. Simplifying the code to resemble what we look at today is going to help us understand how we can take advantage of parallel processing and improve the training performance and therefore the capacity of our neural network. Before we get started though, I'd like to take a moment to make a brief announcement, and that is I've decided to start a Patreon campaign dedicated to artificial intelligence experiments and educational material. So I'll be starting out with a re-edit of this video series, which will be moving to Patreon, and it'll have fewer recordings of me coding in the IDE, but more explanation and illustration to make up for it. So hopefully you'll enjoy watching that series too. Not only have I started this Patreon channel, but in preparation for it, I've also built a dedicated AI computer which uses GPUs to do the processing. Currently, this AI computer, which I've named Queeg, is running 3 AMD RX 580 graphics cards, which are actually quite difficult to obtain right now due to cryptocurrency mining. Soon enough, I'll have 4 cards in that machine, and there's an ultimate goal of 13 graphics cards. Eventually, I'll be upgrading from the AMD RX 580s, possibly to NVIDIA cards or whatever is the latest available card when I have the opportunity to do that. Now, obviously, building a machine like this is expensive, and that's where you can help. Consider subscribing to my Patreon channel and donating as little as $1 per video, or with a monthly cap, just $1 a month, and your money will help to upgrade this computer, as well as help to improve the quality and frequency of my videos. In return, I'll continue to create AI-related videos for both education and entertainment, and as a subscriber, you'll have access to all of my videos early, as well as access to subscriber-exclusive content. So this Patreon channel is brand new, but in time, there will be additional rewards for subscribers as well, as I'll explain in the channel introduction videos. So if you don't wish to subscribe right now, that's fine, but please go take a look at the intro video. At least you'll know what you're going to be missing out on. To learn more, go ahead and click on the link, which is either embedded at the bottom of this video or is in the description below, depending on where you're watching it. Thanks for considering my Patreon campaign, and now on with today's video on neural networks. So this is the neural network which we've developed earlier in this video series. It's the one that I've modeled out in Excel as well as committing to the code, and it's the network that we've used to validate our results so far. In the previous video, we completed the code to build and train this network model. However, in an effort to avoid the math and notation, which is usually used in neural networking tutorials, I chose to simply provide the equations that would work and show them working at each step of the simulation. Today, I'd like to begin introducing some of the simple notation. Now, don't worry, it's really easy stuff. It's just some simple matrix and vector notation. But in doing it this way, we'll simplify the way that we look at this model, and subsequently we can simplify the code to match. So this is going to allow us to more easily transition to parallel processing later on. To start with, let's take a look at the input values that go into H1 in the hidden layer. Via the weights highlighted in red, we can see that the input neurons N1 and N2 are used in the calculation of the value for H1. So we'll take these values and put them into a vector, simple column vector. This vector also has a 1 at the bottom, and this is because, as well as the 2 input neurons, we also have a bias value which is added to the hidden layer. So to simplify the model, the bias value is presented as a weight on a synapse or on an edge, and that's leading into the hidden layer. Now in our case, the value leading into H1 and H2 is the same bias value. So to simplify the math here, we can put an imaginary 1 before the synapses that carry that bias into the hidden layer. And the reason for that is quite simple. 1 multiplied by anything else results in the same value. So in our example, the bias of 0.35 after it's multiplied by 1 is still 0.35. So after we've copied our actual input values into our vector, we also copy the value of 1 for the input to the bias synapses. So let's plug in real numbers for this vector. Here you can see that we have the values 0.05 for N1 and 0.10 for N2 in our vector, as well as that hard-coded 1 for the bias. So now let's consider the weights involved in the input to H1. If we take each of the weights in order, starting with our actual inputs first and then our bias value, we'll get the first row of what will be a 3-row matrix, W1, W2 and B1. So let's repeat this step for the second hidden layer neuron. As you can see, the input values for H2 are the same inputs for H1, and so our input vector doesn't need to change. It never should need to change, because every neuron in the hidden layer is connected to every neuron in the input layer. So what we do is we take the weights and we plug those weights into our matrix as the second row, so W3, W4 and B1. So far we have a vector representing the inputs vertically and a matrix in which each row represents a hidden layer neuron, and the columns contain the weights for that neuron. So let's complete the third row of the matrix. In order to complete this third row, since there are no remaining hidden layer neurons, we plug in values from what's called the identity matrix. You can think of the identity matrix as being a good default state for any matrix that you create. For example, on the right we have a 4x4 identity matrix. The matrix is filled with zeros and has a diagonal line of ones running across it. And this would remain the same even if the dimensions of the matrix were to change. So in our case, for the 3x3 matrix that we're using, before putting in the weights and the biases, the matrix would be initialized with zeros and a diagonal line of ones. Now we've imposed our weights and biases onto the two rows, the top two rows, but the third row remains unchanged from that default state, so it's in the identity state. Incidentally, a vector is actually just a single column matrix, so the 1 inserted at the bottom of our input matrix is essentially there for the same reason. So we now have a complete input vector and a complete matrix representing the hidden layer calculation. So let's get the real values plugged in for that matrix. So now that we have these numbers, what do we do with them? Well, we simply multiply the vector by the matrix, and what we get as a result will be the summation values for our hidden layer. Now when you multiply a vector by a matrix, the result is another vector. So let's take a look. If you're already familiar with how to do this matrix and vector multiplication, feel free to skip ahead, but for those of you that do not, we'll briefly step through this calculation. So we start at the top left of our matrix and at the top entry in our vector. So we have the values W1 from the matrix and N1 from the input vector. We simply multiply these two values together. We then move horizontally across our matrix and vertically down our vector, so we get the values of W2 and N2, which we also multiply together, and we add that to the result from the first step. We're going to repeat this step, moving horizontally across our matrix and vertically down the vector, and we now have a complete first value for our result vector. So let's move on to the next row of the matrix. So we start back at the top of the vector, but we're at the first item in row 2 of our matrix, so we get W3 and N1, and we multiply them together. Again, we move horizontally across the matrix and vertically down the vector, and once more we have row 2 of our output vector. So let's repeat this one more time for the final row of the matrix. So we're back at the first entry in our input vector and the first item in the final row of the hidden layer matrix. We move horizontally along the matrix and vertically down the vector, and now we have the calculation for the final part of our result vector. So after plugging in the real values, we have a result vector containing 0.3775 and 0.3925 and a value of 1. Well, okay, but what do we do with these numbers? Well, let's start by labeling this result vector as A, and what we do now is use our sigmoid activation function on the top two values in vector A. So we're getting the sigmoid of vector A. This gives us the values for H1 and H2. So if you take a look there, you'll see 0.5932699 and 0.5968843. These are the values for H1 and H2 after we've done their initial calculation. So we've only performed this sigmoid function on the first two values in the result vector because we only have two neurons, and therefore we only have two places that the sigmoid activation function takes place. So what do we do for the final value, that hard-coded 1 at the bottom of our results vector? Well, we simply copy it across into the final vector. So we now have a vector which represents values in the hidden layer. If we were to repeat this calculation for the output layer using the weights of W5 through W8, the input to that calculation would be the vector that we just calculated. It's even carried the hard-coded 1 value, which will now be the input for bias 2. So I hope that helps to clarify the forward calculation And if you consider the code to represent this model, you can see how the data types, let's say structs and records, could be created to represent the vectors and matrices. A function to perform multiplication between a vector and a matrix could be easily parallelized because its output vector is not used during the calculation, it's only used to store the results. And as an additional aside, the backpropagation algorithm for training this network can be turned into a matrix operation also, and therefore the backpropagation algorithm can be simplified in a similar way. In another video, we'll take a look at backpropagation as a matrix operation, and then perhaps we'll rewrite our simulation code to reflect this new model of thinking. Until then, I'm Craig Chapman, and thanks for watching. And don't forget to check out my Patreon channel. Thank you.